was the summer of 1950, and the man who had helped split the atom was about to ask a question that would haunt humanity for the next 75 years. Enrico Fermi, Nobel laureate, architect of the world's first nuclear reactor, key contributor to the Manhattan Project, was walking to lunch at the Fuller Lodge in Los Alamos, New Mexico. He was surrounded by some of the most brilliant minds of his generation. Edward Teller, who would later become known as the father of the hydrogen bomb. Emil Konopinski, who studied the structure of atomic nuclei, and Herbert York, future director of Lawrence Livermore National Laboratory. They were joking about flying saucers. Someone had brought up a recent New Yorker cartoon showing cheerful little green aliens stealing trash cans from the streets of New York City. The physicists laughed about it, speculating whether such visitors could travel faster than light. Teller later recalled that Fermi asked him, with characteristic playfulness, what he thought the odds were of faster-than-light travel becoming possible within 10 years. Teller said 1 in a million. Fermi thought that estimate was far too low. Then the conversation moved on to other topics. They sat down to lunch. And that's when Fermi suddenly blurted out a question that, depending on which colleague you ask, was remembered as, "Where is everybody?" Or, "Don't you ever wonder where everybody is?" Or simply, "But where is everybody?" Everyone at the table knew exactly what he meant. Here was the puzzle. Our galaxy contains somewhere between 100 billion and 400 billion stars. Many of those stars are far older than our Sun. If intelligent life can emerge once, as it clearly did here on Earth, then statistically speaking, it should have emerged countless times before us across the vast expanse of cosmic time. Some of those civilizations would have had billions of years to develop technology, to spread across the stars, to leave some detectable signature of their existence. The galaxy is only about 100,000 light-years across. Even traveling at a tiny fraction of the speed of light, a civilization could theoretically colonize the entire Milky Way in just a few million years, a blink of an eye compared to the galaxy's 13 billion-year history. So, where is everybody? Fermi reportedly did some back-of-the-envelope calculations right there at the lunch table. Given the apparent abundance of potentially habitable worlds, given the age of the galaxy, given what seemed like reasonable assumptions about the emergence of intelligence, Earth should have been visited by now. Not just once, many times over. And yet the evidence for such visits was exactly zero. This became known as the Fermi paradox. But here's what makes it genuinely terrifying. Fermi himself, 4 years before his death from cancer in 1954, apparently came up with 3 possible explanations for the silence. According to York's later recollections, Fermi suggested that either interstellar travel was impossible, or advanced civilizations had judged it not worth the effort, or, and this is the one that should keep you awake at night, technological civilizations simply don't last long enough. That last option is called the Great Filter, and if it's true, it means something is systematically killing civilizations before they can spread across the stars. The question is whether we've already passed through that filter, or whether it's still waiting for us ahead. To understand why the silence is so strange, we first need to appreciate how cosmically ordinary our situation actually is. In November of 1961, a decade after Fermi's famous lunch, a young radio astronomer named Frank Drake convened a small gathering at the Green Bank Observatory in West Virginia. The year before, Drake had conducted humanity's first modern search for extraterrestrial intelligence, a project he called Ozma, after the princess in L. Frank Baum's Oz books. For several weeks, he had pointed an 85-foot radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani. Listening for artificial signals, he heard nothing, but the attempt had generated enormous interest, enough that the National Academy of Sciences asked him to organize a conference on the scientific search for intelligent life. Drake invited about a dozen of the world's leading scientists to Green Bank, including a young postdoctoral researcher named Carl Sagan, who at 27 was the least distinguished person in the room. Also present was the biochemist Melvin Calvin, who would win the Nobel Prize in Chemistry during the conference itself for his work on photosynthesis. There was Philip Morrison, a physicist who had worked on the Manhattan Project and had co-authored an influential 1959 paper arguing for exactly the kind of SETI program Drake had undertaken. A few days before the conference began, Drake realized he needed an agenda, some way to structure the discussion around the seemingly impossible question of how many civilizations might be out there. So he wrote an equation. It started with the rate at which new stars form in our galaxy, then the fraction of those stars that have planets, then the number of planets per star system that could potentially support life, then the fraction of those planets where life actually develops, then the fraction of life-bearing planets that develop intelligence, then the fraction of intelligent species that develop technology capable of interstellar communication, and finally, the average lifetime of such a civilization while it's actively broadcasting signals into space. Multiply all these terms together, and you get the number of detectable civilizations in the galaxy right now. Drake wrote the equation on a blackboard the morning of November 1st, 1961, and for the next 3 days, the assembled scientists debated each term. What surprised them was how uncertain they were about nearly everything except the first term. They knew roughly how many stars were forming. Beyond that, they were essentially guessing. And yet, even with wildly conservative estimates, the numbers were striking. The attendees concluded that approximately one new civilization capable of interstellar communication might emerge somewhere in the galaxy each year, which meant the total number of such civilizations existing right now depended almost entirely on that final variable. How long do civilizations last? Philip Morrison found this deeply unsettling. He pointed out that humans had developed a global society, radio telescopes, and interplanetary rockets at roughly the same moment in history that we'd gained the capability to destroy ourselves with nuclear weapons. Perhaps this was typical. Perhaps all civilizations become visible to the wider cosmos at roughly the same time they gain the ability to end their own existence. If the average civilization lasts only about 10 years after achieving radio astronomy, Morrison estimated, then at any given moment, there would most likely be only one communicative civilization in the entire galaxy: us. At the conference's end, the observatory's director, Otto Struve, offered a toast to the value of L. May it prove to be a very large number. The Drake equation has been called the second most famous equation in science, after Einstein's E equals mc squared. It's appeared in countless textbooks, television programs, and popular science books. Frank Drake himself lived to see it become a cultural phenomenon. He died in 2022 at the age of 92, having spent more than 60 years searching the skies for signals that never came. But here's what's often lost in popular discussions of the equation. Drake never intended it as a precise calculation. It was, as he later put it, a great way to organize our ignorance. The equation doesn't give us an answer. It shows us what we need to know to find one. And 65 years after that first meeting at Greenbank, we now know vastly more about most of the terms than Drake and his colleagues could have imagined. What we've learned makes the silence even more disturbing. The Kepler Space Telescope, which operated from 2009 to 2018, discovered over 2,800 confirmed exoplanets and identified thousands more candidates. Before Kepler, we didn't know whether planets were common or rare around other stars. Some astronomers suspected that our solar system might be unusual, that most stars might be alone in the void, without worlds to call their own. Now we know this couldn't be further from the truth. The data suggests that virtually every star in our galaxy has at least one planet orbiting it. But Kepler told us something even more remarkable. According to research published in 2020 by NASA scientist Steve Bryson and his colleagues, roughly half of all Sun-like stars in the Milky Way could have a rocky planet in their habitable zone, the region where liquid water could exist on a planet's surface. Their analysis suggested there are at least 300 million potentially habitable worlds in our galaxy alone. Some of these could be our interstellar neighbors, with the closest likely within just 20 light-years of Earth. A separate study by researchers at the University of British Columbia estimated there could be as many as 6 billion Earth-like planets in the Milky Way, approximately one potentially habitable world for every 5 Sun-like stars. Meanwhile, if you include the far more numerous red dwarf stars, estimates of potentially habitable planets rise to 40 billion or more. Think about those numbers for a moment. Not millions, billions of potentially Earth-like worlds in our galaxy alone. And there are at least 2 trillion galaxies in the observable universe. These aren't wild speculations. These are peer-reviewed analyses of actual observational data collected by spacecraft humanity, built and launched into the heavens. So we return to Fermi's question with new information that makes it even more pointed. If there are hundreds of millions or billions of potentially habitable planets in our galaxy, and if the galaxy is over 13 billion years old, and if Earth-like conditions emerged on even a tiny fraction of those worlds, then where is everybody? The standard response is that we simply haven't looked hard enough yet. Frank Drake himself made this point repeatedly. When people complained that SETI had been searching for 60 years without finding anything, Drake would patiently explain that the amount of searching we've actually done has barely touched the number of possibilities that exist. The stars, the radio frequencies, the channels, the directions. We've only covered a tiny, tiny fraction of all the places where signals might be hiding. To understand just how limited our searches have been, consider the scale of the problem. The Milky Way contains several hundred billion stars. Each star could be broadcasting signals on any of billions of possible radio frequencies. Those signals could be pointing in any direction, encoded in any way, following any transmission schedule. The combination of possibilities is almost inconceivably vast. Drake's original Project Ozma in 1960 observed just 2 stars for a few weeks each, listening near a single frequency. That's like searching for a specific grain of sand on a beach by examining one handful of sand in one spot. Subsequent SETI projects have expanded the search enormously, but the haystack keeps growing with our understanding of it. The search for extraterrestrial intelligence at the University of California, Berkeley, known as SETI at Home, enlisted millions of home computers to analyze radio telescope data from 1999 to 2020. The program detected billions of signals, all of which turned out to be radio frequency interference from human technology rather than extraterrestrial transmissions. The Breakthrough Listen project, launched in 2015 with $100 million in funding from entrepreneur Yuri Milner, represents the most comprehensive and well-funded SETI program ever undertaken. Using the Green Bank Telescope in West Virginia, the Parkes Observatory in Australia, and other facilities, Breakthrough Listen has examined thousands of nearby stars across billions of frequency channels. It has detected nothing clearly artificial. This is true. The sky is vast, the electromagnetic spectrum is broad, and our instruments can only sample a minuscule portion of both at any given time. The Breakthrough Listen project, despite being unprecedented in scope, can only examine a small fraction of the cosmic haystack. But this response, while accurate, is also somewhat beside the point. Because the Fermi paradox isn't really about radio signals, it's about the absence of any evidence whatsoever for intelligence beyond Earth. We're not just failing to pick up broadcasts. We're failing to see megastructures. We're failing to find artifacts in our own solar system. We're failing to detect the waste heat that any sufficiently advanced civilization would inevitably produce. We're failing to observe any of the signatures that a galaxy teeming with intelligent life should have left behind over billions of years of cosmic history. Let me explain what I mean by that. In 1964, the Soviet astronomer Nikolai Kardashev proposed a scale for measuring the advancement of civilizations based on their energy usage. A Type 1 civilization can harness all the energy available on its home planet, about 10 to the 16th power watts for an Earth-like world. A Type 2 civilization can harness all the energy of its star, about 10 to the 26th power watts for a Sun-like star, typically through enormous engineering projects like a Dyson sphere or swarm. A Type 3 civilization controls the energy of an entire galaxy, about 10 to the 36 power watts. Humanity currently registers as roughly Type 0.72 on the Kardashev scale. We use only a tiny fraction of the energy available on Earth, let alone the energy streaming from the Sun. But here's the thing. Any civilization that climbs the Kardashev ladder would leave unmistakable signatures. A Type 2 civilization would partially or fully enclose its star, blocking visible light but radiating enormous amounts of waste heat in the infrared. A Type 3 civilization would be visible across intergalactic distances, a galaxy whose infrared emission was completely different from what we'd expect from natural processes. Astronomers have looked for these signatures. In 2015, researchers analyzed data from the Wide Field Infrared Survey Explorer and concluded that Kardashev Type 3 civilizations are either very rare or do not exist in the local universe. If there were even one galaxy-spanning civilization within a few 100 million light-years of us, we would likely see evidence of their vast engineering projects. We see nothing. The universe is old. The universe is vast. And the universe, as far as we can tell, is completely silent. In 1996, an economist named Robin Hanson proposed a framework for thinking about this silence that has become one of the most influential ideas in the field. He called it the Great Filter. Hanson's argument was elegant and disturbing. We can imagine a series of steps that would need to occur for dead matter to eventually give rise to a civilization that colonizes the galaxy. These steps might include the formation of a star system with the right conditions for life, the emergence of self-replicating molecules, the development of simple single-celled life, the evolution of complex cells with nuclei, the appearance of sexual reproduction, the emergence of multicellular organisms, the development of intelligence, the creation of civilization and technology, and finally, the expansion to become a galaxy-spanning civilization. Hanson listed 9 specific steps in his original essay, though the exact number isn't crucial. What matters is the logic. We observe that such galaxy-spanning civilizations apparently don't exist, or at least haven't contacted us or left obvious traces. This suggests that somewhere along this chain of steps, there must be a filter, some barrier that's extremely difficult to pass. Either one of these steps is fantastically improbable, making intelligent civilizations vanishingly rare, or civilizations that reach a certain point tend to destroy themselves before they can spread to the stars. The crucial question is, where does the filter lie? If the Great Filter is behind us, if it's something like the origin of life itself, or the evolution of complex cells, or the development of intelligence, then we may be one of the very few civilizations that ever made it this far. We beat the odds. The universe is quiet because hardly anyone else exists. This would be wonderful news for humanity's long-term prospects. If we're already through the hardest part, then there's nothing systematic stopping us from becoming a spacefaring species. Our future is limited only by our own choices. But if the Great Filter lies ahead of us, if civilizations regularly arise, develop technology, and then destroy themselves, then the silence carries a much darker message. It means that the very technologies that make a civilization detectable also tend to make it unstable. It means that something about reaching our level of development is inherently self-terminating, and it means we're probably not going to make it. Hanson pointed out a counterintuitive implication of this logic. Finding evidence of life elsewhere in the universe would actually be bad news. If we discovered bacteria on Mars or Europa, it would suggest that the early steps in the evolution of intelligent life aren't as improbable as we might have hoped. That would mean the Great Filter is more likely to lie in our future rather than our past. The more successful life is at getting started, the worse the odds that we'll survive what comes next. This is why some scientists have argued, only half-jokingly, that we should hope Mars is completely sterile, a dead rock where life never got a foothold. That would suggest that abiogenesis, the origin of life, is the hard part. And if that's the hard part, then we've already passed through the filter. Where might the filter be located? Let's examine the candidates more carefully, starting with the very beginning. The origin of life itself. what scientists call abiogenesis, remains deeply mysterious. We know that Earth formed approximately 4.5 billion years ago, and that the earliest evidence of life appears remarkably quickly afterward, perhaps within the first few 100 million years after the planet cooled enough to have liquid water on its surface. In 2017, researchers reported possible evidence of microbial life in rocks from the Nuvvuagittuq greenstone belt in Quebec, Canada, dating back at least 3.77 billion years and possibly as old as 4.28 billion years. If this finding holds up to scrutiny and it remains controversial, it would mean life emerged on Earth almost as soon as conditions allowed. The planet finished forming, cooled down, developed oceans, and life appeared, all within a few 100 million years. This speed has traditionally been taken as evidence that abiogenesis might be relatively easy, that given the right conditions, life emerges quickly. If it were vanishingly improbable, you might expect it to take much longer or not to happen at all within Earth's habitable window. The origin of life question has inspired decades of experimental work attempting to understand how chemistry could become biology. The landmark 1952 Miller-Urey experiment, conducted by Stanley Miller and Harold Urey at the University of Chicago, demonstrated that amino acids, the building blocks of proteins, could form spontaneously when an electrical discharge was passed through a mixture of gases thought to resemble Earth's early atmosphere: methane, ammonia, hydrogen, and water vapor. The result electrified the scientific community. Here was evidence that the complex molecules necessary for life could arise from simple inorganic precursors given the right conditions. Subsequent experiments, both on Earth and in space, have shown that amino acids can form in a wide variety of environments: in interstellar clouds, on meteorites, in the plumes of hydrothermal vents. But here's the crucial gap that remains largely unexplained. Amino acids are not life. They're not even close to life. The simplest living cell is an extraordinarily complex system containing thousands of different molecular machines working in precise coordination. DNA for storing information, RNA for transcribing it, ribosomes for translating it into proteins, membranes for containing everything, ATP for energy transfer, and countless regulatory mechanisms for coordinating all of these processes. How did such complexity arise from mere chemistry? This is the hard problem of abiogenesis, and despite decades of brilliant research, we still don't have a satisfying answer. Researchers have proposed various scenarios. The RNA world hypothesis suggests that early life was based on RNA molecules that could both store genetic information and catalyze chemical reactions, with DNA and proteins evolving later as more efficient specialists. The metabolism first theories propose that networks of chemical reactions developed the ability to sustain and reproduce themselves before genetic molecules existed. The hydrothermal vent theories locate the origin of life at deep-sea volcanic vents, where chemical gradients could have provided the energy needed to bootstrap living systems. Each of these hypotheses has strengths and weaknesses, supporters and critics. None has been demonstrated to fully explain the transition from non-living chemistry to living cells. The gap between our most successful origin of life experiments and the simplest known cells remains enormous, but there's a statistical problem with this reasoning that the astronomer David Kipping has highlighted. The fact that we exist to observe the early emergence of life on Earth creates a selection effect. We could only find ourselves on a planet where life arose early enough for intelligence to evolve before the sun makes Earth uninhabitable. This doesn't tell us how probable abiogenesis is on planets in general. Furthermore, we still don't understand the mechanism by which non-living chemistry gave rise to the first self-replicating molecules. We simply don't know whether the origin of life is easy, requiring only the right chemical conditions to emerge almost inevitably, or hard, requiring an extraordinarily improbable sequence of events. If it's hard, then life might be rare throughout the cosmos, and the filter would lie very early in the sequence. Earth would be one of the lucky few, and the silence would reflect genuine cosmic emptiness. But even if abiogenesis is rare, it only needs to happen once on a planet for that world to become populated with life. Given billions of potentially habitable worlds in our galaxy alone, even very low probabilities add up. So let's move on to the next potential filter. The transition from simple cells to complex cells is a leading candidate for the great filter among biologists. Here's why. For roughly 2 billion years after life first appeared on Earth, nothing much happened. Bacteria and their cousins, the archaea, dominated the planet, floating in the oceans, forming mats on rocks, exchanging genetic material, but never developing the kind of complexity that would eventually lead to multicellular organisms. This period is sometimes called the boring billion, though that's a bit unfair to the bacteria, who were busy oxygenating the atmosphere and reshaping the planet's chemistry. Then, somewhere between 2.1 and 1.5 billion years ago, something extraordinary occurred. One type of cell engulfed another type of cell, and instead of digesting it, formed a permanent partnership. The engulfed cell became the mitochondrion, the powerhouse that provides energy to complex cells through aerobic respiration. This event is called endosymbiosis, and understanding its significance requires grasping just how different eukaryotic cells are from their bacterial ancestors. A typical bacterium is like a simple factory, genetic material floating in a soup of proteins and metabolic machinery, all enclosed by a membrane. It works, but it's limited in what it can achieve. A eukaryotic cell is something else entirely. It has a nucleus, a membrane-bound compartment where genetic material is organized and protected. It has an extensive internal membrane system for processing proteins and lipids. It has a cytoskeleton that gives the cell structure and allows it to change shape, engulf particles, and divide with precision. Most crucially, it has mitochondria, hundreds or thousands of them, churning out the energy currency that powers all this complexity. Where did all this machinery come from? The most compelling answer, supported by overwhelming genetic evidence, is endosymbiosis. The mitochondria in your cells were once free-living bacteria that somehow found themselves inside a host cell and established a permanent partnership. Similarly, the chloroplasts in plant cells, the organelles responsible for photosynthesis, descended from captured cyanobacteria. As far as we can tell from the fossil record and genetic evidence, this happened only once in the entire history of life on Earth. Every complex multicellular organism alive today, every plant, animal, fungus, and protist descended from that single primordial merger. We're all children of the same improbable union. The biochemist Nick Lane at University College London has argued extensively that this suggests eukaryogenesis might be extraordinarily improbable. Lane points out that bacteria have existed for billions of years across countless planetary environments, and they've never independently evolved the internal complexity of eukaryotic cells. They've developed impressive capabilities. Some can photosynthesize, some can fix nitrogen, some can survive extreme heat or radiation, but they've never developed nuclei, mitochondria, or the other organelles that characterize complex cells. If the origin of the eukaryotic cell was not a bottleneck, Lane wrote, then it was probably a genuinely unlikely sequence of events, for it happened only once. Speaking as a multicellular eukaryote, I might be biased, but I do not believe that bacteria will ever ascend the smooth ramp to sentience, or anywhere much beyond slime, here or anywhere else in the universe. If Lane is right, the filter might have been the emergence of complex cells. Bacteria might be common throughout the universe. We might eventually find them on Mars, Europa, Enceladus, in the clouds of Venus, on countless exoplanets. But anything more sophisticated might be vanishingly rare. This is, in some ways, a hopeful scenario. It suggests the hard part is behind us, but we can't be certain. Let's move further along the chain. What about the evolution of multicellular life? Here, the story becomes more complicated. We now know that multicellularity evolved independently many times on Earth, at least 50 separate origins, according to some estimates. Simple multicellular structures like bacterial mats and filaments appeared very early, possibly over 3 billion years ago. More complex multicellular organisms evolved later, but still multiple times. In 2024, researchers published evidence of a 1.63 billion-year-old multicellular eukaryote called Chinchania magnifica, pushing back the timeline for multicellular complexity by nearly 1 billion years from previous estimates. This suggests that once complex cells exist, the jump to multicellular organization might not be as difficult as once thought. But there's a catch. Simple multicellularity is one thing. The kind of complex multicellularity we see in animals, plants, and fungi, with many specialized cell types, sophisticated developmental programs, and integrated organ systems, is something else entirely. Complex multicellularity has evolved only 5 times independently in Earth's history, all within eukaryotes. It's never evolved in prokaryotes. Furthermore, complex multicellularity appears to require large genomes and sophisticated gene regulation, which in turn seems to require the energy abundance that mitochondria provide. This brings us back to the eukaryotic transition as a potential bottleneck. So multicellularity per se might not be a filter, but complex multicellularity, the kind that can eventually lead to brains and technology, might be far more constrained than simple cell cooperation. What about intelligence? This is perhaps the most contentious potential filter of all. Earth has hosted billions of species across hundreds of millions of years of evolution. Countless evolutionary lineages have explored countless ecological niches, and only one, us, has developed technology capable of sending signals into space. The biologist Ernst Mayr, one of the architects of the modern evolutionary synthesis, repeatedly emphasized this point. Intelligence, as measured by technological capability, is not some inevitable endpoint of evolution. It's a specific adaptation that arose in specific circumstances. The ancestors of humans happened to be social primates in Africa who faced particular environmental pressures that favored larger brains and more sophisticated tool use. 1 million small accidents of evolutionary history had to fall in just the right way. From this perspective, the emergence of technological intelligence on any given inhabited planet might be extraordinarily improbable. The fraction of life-bearing planets that develop intelligence might be vanishingly small. But there's a counter-argument. Evolution on Earth has produced intelligence, or at least sophisticated cognition and problem-solving ability, multiple times independently. Cephalopods, like octopuses, have evolved complex nervous systems and remarkable cognitive abilities on a completely separate branch of the animal family tree. Corvids, crows, and ravens show tool use and problem-solving that rivals great apes. Cetaceans, whales, and dolphins have enormous brains and complex social behaviors. None of these lineages developed technology as we understand it, but they suggest that there might be multiple evolutionary pathways towards sophisticated cognition, even if only one of them happened to lead to radio telescopes and rocket ships. We simply don't know. This is one of the central uncertainties in the Drake equation, and it may remain uncertain until we find evidence of intelligence elsewhere, or until we've searched long enough that the absence of such evidence becomes evidence of absence. All of these represent potential pass filters, barriers we may have already crossed. If any of them are truly formidable, we might be extraordinarily rare, perhaps unique in the observable universe. The silence would simply reflect the cosmic loneliness of our situation. But what if we're not rare at all? What if civilizations arise with some regularity, develop technology, and then what? This is where the conversation takes a darker turn. Consider our own history. In 1945, humanity demonstrated that it could destroy cities with a single weapon. The atomic bombs dropped on Hiroshima and Nagasaki killed over 200,000 people and ushered in an era of existential threat that continues to this day. Within 2 decades of Hiroshima, we had built arsenals capable of ending civilization in an afternoon. At the peak of the Cold War, the United States and Soviet Union possessed roughly 70,000 nuclear warheads between them. The Cuban Missile Crisis of October 1962 brought us to the brink of nuclear war. According to some accounts, we came closer to annihilation than most people realized at the time. We didn't destroy ourselves, but we came close. And that was just the beginning. In the years since the Cold War's end, the nuclear threat has evolved rather than disappeared. Russia and the United States still maintain thousands of nuclear warheads on hair-trigger alert, capable of being launched within minutes. The doctrine of mutually assured destruction still underlies international relations between nuclear powers, and the club of nuclear-armed nations has grown, adding China, Britain, France, Israel, India, Pakistan, and North Korea, with others potentially aspiring to join. Meanwhile, entirely new categories of existential risk have emerged. The philosopher Toby Ord, in his 2020 book, The Precipice, estimated that the probability of human extinction within the next century might be as high as 1 in 6, roughly the odds of dying from Russian roulette. Most of that risk comes not from natural disasters, but from technologies of our own creation. Nuclear weapons, engineered pandemics, artificial intelligence systems that might pursue goals misaligned with human flourishing. Consider engineered pandemics. The COVID-19 pandemic demonstrated how a natural virus can spread globally within weeks, overwhelming healthcare systems and disrupting civilization. Now, consider what might happen if someone deliberately engineered a pathogen for maximum lethality and transmissibility, optimized to spread asymptomatically for weeks before killing its hosts, resistant to existing treatments, perhaps designed to mutate and evade vaccines. The knowledge and tools to create such pathogens are becoming increasingly accessible. What once required state-level resources and specialized facilities can increasingly be done with equipment available to individual researchers. This democratization of biotechnology brings many benefits, but it also creates unprecedented risks. Or consider artificial intelligence. The systems we have today are already capable of producing text, images, and code that were beyond imagination just a few years ago. The trajectory of AI capability has consistently exceeded predictions. At some point, perhaps in years, perhaps in decades, we may develop artificial general intelligence, systems that match or exceed human cognitive abilities across all domains. Such systems could be enormously beneficial, helping us solve problems from climate change to cancer, but they could also pose catastrophic risks if their goals become misaligned with human flourishing. Not because they become malevolent in some Hollywood sense, but simply because they optimize for objectives that turn out to be subtly wrong when pursued with superhuman capability. The philosopher Nick Bostrom has observed that humanity's relationship with existential risk is unlike anything we've encountered before. Throughout most of our history, the risks we faced were local. They might devastate a region or destroy a civilization, but they wouldn't end the human story entirely. The Roman Empire fell, but humanity continued. The Black Death killed a third of Europe's population, but humanity continued. Countless cultures have risen and collapsed, and the species endured. Now, for the first time, we possess the capability for true extinction, the permanent termination of all human potential, and our capabilities continue to grow. Here's the truly frightening part. The technologies that create these risks are the same ones that make us detectable to the cosmos. Radio astronomy and nuclear weapons emerged at essentially the same moment in human history. The same physics that allows us to send signals across interstellar distances also allows us to annihilate cities. The same understanding of the atom that powers our communication satellites could power weapons capable of rendering our planet uninhabitable. This pattern extends beyond nuclear technology. Advanced biotechnology could cure diseases or create unstoppable plagues engineered for maximum lethality and transmissibility. Artificial general intelligence could solve our hardest problems or pursue optimization goals that leave no room for human values or even human existence. What if this pattern is universal? What if technological civilizations everywhere face a narrow window, perhaps just a few centuries, during which they've developed enough capability to be noticed, but haven't yet developed the wisdom to survive their own power? Philip Morrison's insight from 1961 gains new force. Perhaps civilizations become visible to the universe at the same moment they become capable of destroying themselves. Perhaps the two capabilities are fundamentally linked, because both require deep understanding of matter and energy at scales far beyond what's needed for mere biological survival. And perhaps most civilizations don't navigate that narrow passage successfully. The physicist Freeman Dyson, who did pioneering work on the physics of hypothetical alien megastructures, once observed that the critical period for any technological civilization might be the first few centuries after it develops nuclear weapons and other weapons of mass destruction. If a civilization can survive that period, if it can develop the institutional wisdom and global coordination to manage its own destructive potential, then it might go on to spread across the stars. But if it can't, if this is true, the silence isn't evidence that we're alone. It's evidence that we're next. There are more hopeful interpretations, of course. The astronomer Seth Shostak of the SETI Institute has suggested that the pessimistic interpretation of the Fermi paradox might be too anthropocentric. We're assuming that alien civilizations would face the same challenges we do, make the same mistakes, succumb to the same temptations. But evolution on other worlds might produce beings with very different psychologies, different social structures, different relationships with technology. Maybe most civilizations manage their nuclear arsenals more wisely than we have. Maybe they develop robust global governance before acquiring weapons of mass destruction. Maybe their evolutionary history produced species that are naturally more cooperative than competitive, more patient than impulsive, more wise than clever. Maybe most find sustainable relationships with their planetary environments, perhaps the kind of short-term thinking that drives human environmental destruction is not universal but reflects peculiarities of our cognitive evolution, adaptations for survival on the African savanna that become maladaptive at civilizational scales. Other species, with different evolutionary histories, might naturally think in longer time horizons. Maybe most develop AI that remains aligned with their values. Perhaps the alignment problem that worries so many researchers is not as hard as we fear. Or perhaps other civilizations approach artificial intelligence development more cautiously, taking centuries rather than decades to develop systems that could pose existential risks. This is a fair point. We're reasoning from a sample size of 1, which is never a good basis for statistical inference. The history of science is littered with examples of humans assuming their local circumstances were universal, only to discover vast diversity where they expected uniformity. But the counter-argument is equally compelling. The fact that we see no evidence of any civilization anywhere suggests that the filter is extremely effective. It's not enough for some civilizations to survive. For us to see the cosmic silence we observe, virtually all civilizations must fail to leave lasting traces. That's a high bar. Furthermore, while alien minds might differ from ours in many ways, certain constraints seem likely to be universal. Any civilization capable of affecting its environment at scale will face the thermodynamic reality that concentrated energy can do tremendous damage. Any civilization that develops powerful technology will confront the fact that such technology can be misused. Any civilization experiencing exponential growth will eventually encounter the limits of its resource base. The specifics might differ, but the general pattern, growing power meeting insufficient wisdom, seems like it might be a recurring theme across the cosmos. There's another possibility worth considering, one made famous by the Chinese science fiction author Liu Cixin in his novel The Dark Forest, the second book of the Three-Body Problem trilogy. What if civilizations exist but deliberately hide themselves? Liu's Dark Forest hypothesis rests on a few simple premises. Survival is the primary need of any civilization. Civilizations continuously grow and expand, but resources are finite. And crucially, you can never truly know whether another civilization is friendly or hostile. Communication across interstellar distances is so slow that by the time you receive a response to your message, the civilization that sent it might have changed completely, developing technology that makes them a lethal threat. In Liu's formulation, the universe is a dark forest. Every civilization is an armed hunter stalking through the trees like a ghost, gently pushing aside branches that block the path and trying to tread without sound. Even breathing is done with care. The hunter has to be careful because everywhere in the forest are stealthy hunters like him. If he finds another life, another hunter, angel, or a demon, a delicate infant, or a tottering old man, a fairy or demigod, there's only one thing he can do: open fire and eliminate them. In this scenario, the universe is like a dark forest where every civilization is a hunter stalking through the trees. If you find evidence of another hunter, the only safe response is to destroy them before they can destroy you. Any civilization that broadcasts its location is signing its own death warrant. It's a bleak vision, one where the silence represents not emptiness, but terror. Everyone is hiding because showing yourself is suicide. The dark forest hypothesis has gained cultural traction, particularly after the Netflix adaptation of Liu's novels. But scientists have raised numerous objections. Would all civilizations really converge on the same paranoid strategy? The physicist and cosmologist Seth Shostak has pointed out that we don't even see such uniformity among human cultures. Some are aggressive, some are cooperative, some are isolationist, some seek trade and contact. Why would all alien civilizations adopt identical postures? Couldn't sufficiently advanced civilizations simply observe other worlds without being detected? If you can build weapons capable of destroying civilizations across interstellar distances, you can probably also build telescopes capable of detecting them. The hiding strategy might be futile against anyone advanced enough to be a genuine threat. And there's a deeper problem. If the dark forest hypothesis is true, and if any sufficiently advanced civilization would seek to destroy competitors, then why hasn't Earth already been sterilized? Our radio signals have been expanding into space for over a century. Our planet's atmospheric signatures have been potentially detectable for billions of years. If there were hunters in the forest, they would have found us by now. Unless, of course, they're on their way. There is one more sobering possibility that emerges from the dark forest hypothesis. Perhaps Earth has been noticed. Perhaps our radio signals, expanding outward at the speed of light since the early 20th century, have already been detected by some ancient civilization lurking in the darkness. And perhaps they're already responding, not with a message, but with something else entirely. At the speed of light, any response from a civilization just 50 light years away would take a century to arrive. We wouldn't know until it was far too late to do anything about it. This is, admittedly, speculative, but it illustrates how the Fermi paradox forces us to confront possibilities we might prefer to avoid. The silence could mean many things. Few of them are entirely comforting. The timescales involved in galactic colonization are actually quite short compared to cosmic history. This is one of the key factors that makes the Fermi paradox so troubling. Even traveling at just 1% of the speed of light, far slower than the relativistic speeds that physics allows, a civilization could traverse the entire Milky Way in about 10 million years. That sounds like a long time on a human scale, but it's only 1/10 of 1% of the galaxy's age. The galaxy has existed for over 13 billion years. 10 million years is a rounding error. Consider a simple model. A civilization develops interstellar travel and sends colony ships to nearby stars, traveling at 1% of light speed. They reach their destinations in a few hundred to a few thousand years. The colonies establish themselves, grow, and eventually send out their own colony ships. The process repeats, even if each colony waits 1,000 years before launching new expeditions, time enough to build infrastructure and population. The expansion would be relentless. Like a chain reaction, each generation of colonies spawns the next. The frontier moves outward at a steady pace. And you don't need everyone to participate. You don't need central coordination. You just need some fraction of each generation to choose expansion over stability. If even 1 in 10 colonies launches new expeditions, the math still works out. Exponential growth is powerful. Under these assumptions, a single civilization could populate every star system in the Milky Way within about 100 million years. That's less than 1% of the galaxy's age. To put this in perspective, if the galaxy were a human life, with the Big Bang at birth and the present day at age 70, then the entire time needed to colonize the galaxy would be less than 8 months. Less than the time between starting kindergarten and finishing first grade. Less than a single school year. And there's no reason to think this colonization would require any technology beyond what we can already envision. We don't need faster than light travel, which may be impossible according to our current understanding of physics. We don't need warp drives or wormholes or any exotic physics. Simple nuclear pulse propulsion, technology that was seriously designed in the 1950s and 60s under Project Orion, could accelerate spacecraft to about 3% of light speed. This is the crux of the paradox. The galaxy is old enough that even a single civilization arising billions of years ago could have expanded to every corner of the Milky Way by now, multiple times over. The fact that we see no evidence of such expansion, no megastructures, no signs of stellar engineering, no artifacts in our solar system, suggests one of several possibilities. Perhaps we truly are alone, the first civilization to reach this point in this galaxy's history. Perhaps we won the cosmic lottery, emerging from the primordial soup at just the right moment to find an empty galaxy waiting for us. Perhaps intelligent life arises, but rarely develops the motivation for interstellar expansion. Maybe most civilizations turn inward, focusing on virtual realities or inner contemplation rather than physical spread across the stars. Perhaps they transcend their biological origins and lose interest in matter and energy as we understand them. Perhaps they discover that the universe is stranger than we imagine, that there are dimensions or realities beyond our perception, and they simply leave our cosmos behind for something we cannot comprehend. Perhaps there's some unknown constraint that makes colonization far harder than our calculations suggest. Maybe interstellar travel is more dangerous or more resource-intensive than we imagine. Maybe the galaxy is full of hazards we haven't yet encountered, natural phenomena that destroy or divert civilizations before they can spread far. Or perhaps civilizations consistently destroy themselves before they can spread, caught in a trap of their own making. their technological capability outpacing their wisdom. Their power to create exceeded only by their power to destroy. As the years pass, new hypotheses accumulate. Perhaps civilizations transcend into digital existence and have no interest in physical expansion. Perhaps they undergo a kind of asymptotic burnout, growing rapidly and then collapsing as they exhaust resources or fail to coordinate. Perhaps there's a galaxy-spanning zoo policy that keeps primitive species like us in quarantine. Perhaps we're living in a simulation, and the apparent emptiness of the cosmos is simply a design choice of our simulators. Each of these ideas has its adherents and its problems. None has emerged as clearly correct. The paradox remains stubborn and unexplained. But among all the possible explanations, the Great Filter stands out for its ominous implications. It tells us that our fate is bound up with the fate of all intelligence in the universe. If civilizations regularly arise and then perish, we need to understand why, because understanding might be the only thing that saves us from the same end. What might that filter look like in practice? Let me paint a few scenarios that keep researchers in existential risk up at night. Consider the challenge of coordination at scale. Human civilization has become a single, interconnected system, dependent on global supply chains, international financial markets, and the continuous functioning of critical infrastructure. This interconnection brings enormous benefits, unprecedented prosperity, rapid communication, shared knowledge, but it also creates systemic fragility. A sufficiently severe shock, a major pandemic, a nuclear exchange, a catastrophic cyber attack, a collapse of the global food system could cascade through the network in ways that are difficult to predict or control. Our optimization for efficiency has often come at the cost of resilience. We've built a civilization that works beautifully under normal conditions, but might be brittle under extreme stress. Or consider the slower burning threats: climate change, environmental degradation, resource depletion. These might not cause sudden extinction, but they could weaken civilization to the point where it becomes vulnerable to other shocks. A society struggling to feed itself and manage mass migration has less capacity to prevent nuclear proliferation or regulate artificial intelligence. Each of these represents a potential filter mechanism. None guarantees extinction, but each narrows the window through which we must pass to achieve a long-term future. In 1984, 3 decades after Fermi's lunch at Los Alamos, physicist Eric Jones tracked down the surviving participants in that fateful conversation and collected their recollections. By then, Fermi had been dead for 30 years, but his question had taken on a life of its own, spawning decades of research, speculation, and increasingly sophisticated attempts to detect evidence of extraterrestrial intelligence. Jones confirmed that the conversation had indeed occurred roughly as remembered, that Fermi had indeed performed his quick calculations, and that the 3 physicists present had each remembered the key question slightly differently. Where is everybody? Or, don't you ever wonder where everybody is? Or, but where is everybody? These subtle variations might actually be significant. The first version suggests genuine puzzlement. The second suggests a chronic sense of unease, a background concern that had been nagging at Fermi for some time. The third suggests frustration, even exasperation, as if the silence were a personal affront to rational expectations. 75 years later, all three reactions seem appropriate. We have spent billions of dollars developing technologies to search the skies for signals. We have launched spacecraft to explore our solar system in unprecedented detail. We have discovered thousands of exoplanets, measured the chemical compositions of their atmospheres, identified hundreds of potentially habitable worlds. We have developed theoretical frameworks for understanding the probability of life, the economics of interstellar expansion, the game theory of cosmic civilizations, and the universe remains silent. This silence is itself a datum, perhaps the most important datum we have. It tells us something profound about the nature of reality, even if we don't yet fully understand what that something is. One interpretation: we are precious beyond measure. Out of all the matter in the observable universe, across billions of years of cosmic evolution, the atoms currently arranged as you, hearing these words, represent something cosmically rare, perhaps cosmically unique. The emergence of consciousness, the development of science and technology, the ability to ask questions about our place in the universe. These might be achievements so improbable that we are, quite literally, alone. Another interpretation: we are in danger beyond measure. The same capabilities that allow us to contemplate the stars are poised to destroy us. The narrow passage we must navigate between developing technology powerful enough to spread across the galaxy and developing wisdom enough to survive that technology might be narrower than we imagine. And the silent stars are silent because no one has navigated it successfully. Both interpretations demand the same response. Treat our existence as the precious, improbable, fragile thing it is. Here is what we know. Life arose on Earth quickly, within the first few 100 million years after conditions allowed it. This suggests that the origin of life might not be the filter, though we cannot be certain. Complex cells took billions of years to evolve from simple cells and appear to have originated only once. This might be a filter, or it might simply reflect our limited understanding of early evolution. Intelligence capable of technology arose only once among billions of species across hundreds of millions of years of evolution on our planet. This might be a filter, or it might be a statistical artifact of small sample size. Technological civilizations, once they arise, have enormous power to transform their environments. This is not speculation. We are doing it right now, for better and worse. Advanced civilizations, if they existed in abundance, should have left detectable traces across billions of years of galactic history. We see no such traces. Therefore, something is filtering civilizations out of existence. The question is what and when. If the filter is behind us in the early stages of life's emergence or evolution, then our future may be bright. We might be destined to become the ancestors of a galaxy-spanning civilization, filling the Milky Way with the descendants of Earth's biosphere. The silent stars would be an opportunity, not a warning. If the filter is ahead of us, in the transition from planetary civilization to interstellar civilization, then our future is uncertain at best. We face challenges that, statistically speaking, most civilizations apparently fail to survive. The silence is a tombstone for countless species who came before us and failed the test we have yet to take. We do not know which scenario is true, but the fact that we cannot dismiss the second possibility should inform how we think about our responsibilities to the future. The stars are silent. We do not know why. Perhaps we are the first, the earliest stirrings of consciousness in a cosmos still young and mostly empty. If so, we carry an awesome responsibility. We are not just one civilization among many, but potentially the only chance the universe has to understand itself through conscious minds. Perhaps we are the next, one more in a long line of species that briefly flickered into technological awareness and then snuffed themselves out, leaving the galaxy dark and quiet for another billion years until the next candidate arose. Our radio signals expanding into the void, unanswered, our monuments crumbling to dust, our story ending not with a whimper, but with silence. Perhaps the truth is something else entirely, something our current understanding cannot accommodate. The universe is vast and strange, and our theories might be as provincial as a medieval peasant's understanding of the stars. But here is what I believe. The silence is not something to be explained away. It is not a puzzle to be solved and filed. It is a warning. For billions of years, the atoms that now comprise human civilization have drifted through space, coalesced into stars, been forged in supernovae, gathered into planets, organized into increasingly complex patterns of matter and energy until, in the blink of a cosmic eye, they became capable of asking where everybody is. This is extraordinary. This might be the most extraordinary thing that has ever happened in our corner of the universe, and the silence suggests that it might be far more fragile than we imagine. Think about what it took for you to exist. A star had to form and burn for billions of years, then explode, scattering heavy elements across space. Those elements had to gather into a new solar system, coalesce into a planet at just the right distance from a stable star. Life had to arise from chemistry through processes we still don't understand. That life had to survive for billions of years through ice ages and asteroid impacts and super volcanic eruptions. Cells had to engulf other cells to form the complex eukaryotes that gave rise to all plants and animals. Multicellular life had to evolve and diversify through mass extinction after mass extinction. Primates had to descend from the trees and develop language and technology. Civilizations had to rise and connect across the globe. And now, here you are, a conscious being made of star stuff, contemplating your place in a universe that, as far as we can tell, is vast and ancient and utterly silent. The improbability of your existence is staggering, and the silence of the cosmos suggests that this improbability might extend far beyond Earth. The conscious technological civilizations might be among the rarest phenomena in the universe. Or it suggests that such civilizations arise but do not last. Fermi asked his question at Los Alamos, the same facility where, just 5 years earlier, humans had first harnessed the energy that powers the stars. The same facility where weapons were being developed that could render our entire species extinct. The juxtaposition was not lost on him or his colleagues. We stand today at a similar juncture. Our capabilities continue to grow exponentially. Our wisdom has not kept pace. The technologies that might carry us to the stars are the same ones that might ensure we never leave Earth at all. The silence of the cosmos is not evidence of cosmic emptiness. It is evidence that we have not yet passed the test. The great filter, whatever it is, wherever it lies, has claimed every civilization that came before us, if any did. We do not know if we will be different. We cannot know until we try. but we can recognize the stakes. We can understand that the question, "Where is everybody?" might have an answer we desperately need to avoid becoming. And we can work with whatever wisdom and determination we can muster to become the exception, the civilization that looked up at the silent stars, understood the warning they represented, and chose to survive. Every generation faces a choice about what kind of ancestors they want to be. Will we be the generation that secured humanity's long-term future, that navigated the narrow passage between developing godlike powers and developing godlike wisdom? Or will we be the generation that stumbled, that failed to see the warning signs, that left nothing behind but silence and ruins? The stakes could not be higher. If we fail, we don't just lose ourselves, we lose everything. The entire future that could have been, the trillions upon trillions of lives that might have flourished across billions of years of cosmic time, the civilizations that might have spread to other stars, seeding the galaxy with consciousness and meaning, the answers to questions we haven't even learned to ask, and perhaps most haunting of all, we lose the chance to answer Fermi's question from the other side. If we succeed, if we spread beyond Earth and become a multiplanetary species, if we eventually reach other star systems and fill the galaxy with life, then someday, some other young civilization on some other world will look up at the night sky and wonder if they're alone. And they won't be, because we'll be there. Our descendants, biological or digital or something we can't yet imagine, will have left our mark across the cosmos. The silence will have been broken. The great question will have been answered, not by discovering intelligence, but by becoming the discoverers ourselves. This is the opportunity that lies before us. This is the burden that the Fermi paradox places on our shoulders. We are not merely asking a scientific question when we wonder where everybody is. We are confronting the most profound challenge in human history, the challenge of becoming a species that can survive its own technological adolescence. The universe is waiting. Somewhere, perhaps, other eyes will look up at distant suns and ask the same question Fermi asked on that summer day in 1950. They will scan the heavens, searching for evidence that they are not alone. And what they find or don't find will depend, in some small measure, on what we do in the decades and centuries ahead. Will they detect the signatures of a thriving civilization spreading outward from a small blue planet in the Orion Arm? Will they find evidence of intelligence that solved the riddle of its own survival? Or will they find only silence, another empty corner of a vast and quiet cosmos, another world that rose briefly toward the light and then fell back into darkness? The answer to that question is not written in the stars. It is not determined by physics or chemistry or the cold equations of probability. It depends on what we choose to do with the time we have and whether we can become the kind of civilization that deserves to inherit the cosmos. It is up to us. The silence of the cosmos is not a riddle to be solved for intellectual satisfaction. It is a mirror held up to our own civilization, asking what kind of future we will choose. Will we be the species that looked up at the empty sky and rose to fill it with life and meaning? Or will we be another failed experiment, another promising beginning that ended in self-destruction? The choice is ours, and the clock is ticking. Every day that passes without us taking seriously the long-term future of our species is a day we might later regret. Every conflict that diverts resources from our shared challenges, every short-term decision that mortgages our future, every failure to cooperate on the existential risks we face, brings us closer to becoming another answer to Fermi's question, another silent world in a silent galaxy. But every day also brings opportunities to build the institutions that could help us survive, opportunities to develop the technologies that could take us to the stars, opportunities to become wiser, more cooperative, more far-sighted than we have ever been before. The Fermi paradox is not just a scientific puzzle, it is a call to action. The universe is waiting to see what we will become.